Okay, welcome back to our second lecture, group of lectures anyway, uh, for Chem 120. Where we left off was section 1.5, so at the moment we're a little bit ahead of schedule, and we'll see if we can keep it that way. Our next section up for discussion is units of measurement. And this is a really important thing in any science, really, because measurement is a major part of science. That's really what we do just about all the time, is we measure stuff. And so first of all, let's start at the very beginning and say, what is a measurement? And measurement is basically where you establish the magnitude of some quantity. Okay, so establishing the magnitude of a quantity, whether that quantity be length or width or height or mass or number of atoms, or number of moles of atoms, as we'll get to in the future. Establishing magnitudes of quantities are a very, very important side of science. Each magnitude or each measurement consists of a number and a unit. And this is something that beginning chemistry students often have trouble remembering. When you're doing a measurement, the number and the unit are both equally important. The number, of course, is important, but a lot of times students will write down the number for a measurement, and then they'll come back to it later when they're writing up the lab report or something like that, and they'll see that number, but they'll have no idea what it is because they didn't write down the units that go with it. So they don't know if it's a volume or a mass or what it is. And so, units are important. What the units do, or what the units are, is basically standardized quantities. They're sort of, units are basically agreed upon standards. So when you measure the length of a piece of paper in inches and you find out that a standard piece of paper is 11 inches long, what you're doing is you're comparing the length of paper to that standard agreed upon unit known as the inch. And you're saying that 11 of these standard agreed upon units are equivalent to the length of the paper. And so that's basically what a unit is. So in more formal terms, they're standard quantities used to convey the relative magnitude and type of measurement. They can do both of these things because there are different units for different types of measurements. So, if you see, say, 11 inches, then you know that that must be a length or a distance of some sort. You know that it's not a mass and it's not a volume. And so that just the units there have conveyed to you what type of measurement it was. And so that's why it would be very useful if students, even if they insist on jotting down data on scrap paper without, instead of in the spaces on the report provided, they should at least take down the units so that they'll have some idea what kind of measurement it was later on. Also, units tend to convey the the relative magnitude of the measurement, because we tend to choose units that will give us a convenient number to go with the unit. So even once you've established that it's a length or a distance that you're measuring, you have a choice among several units to use. Just within the English system, you could use inches or feet or yards or miles. And so you tend to choose whichever unit will give you the most convenient and reasonable size number. You're probably not going to measure the length of a piece of paper in miles. You'd end up with a ridiculously small number because miles are huge compared to the size of a piece of paper. So you're probably going to use either inches or feet for a piece of paper. But if you're measuring the distance from, here to Rochester, you're not going to use inches unless you really want to deal with a really huge number. You're probably going to use miles because that gives you a much more reasonable number. It's about 60 miles. Yeah, we tend to choose which unit gives us the most convenient size number to go with it. And as I kind of alluded to in that last bit about the English system of measurement, there are different systems of units. The main ones being the English system and the metric system, both of which we'll go over in more detail in a moment. But there are other systems too. And actually, it turns out, as we'll see, that even in the metric system, there are kind of different systems or different subsets of units within the metric system. And so unit conversions are very important. We'll go over some unit conversions in a little while. There are some more examples in the text and in the homework problems. It's a very important skill to have. Unfortunately, this being a summer course, we don't have a lot of time to review that kind of thing. So hopefully you'll be able to pick it up if you haven't done this kind of thing before. Hopefully you have done it before. But unit conversions are very important for several reasons. You can have unit conversions between the English and metric systems. They're very important because we in this country tend to measure things in everyday life using the English system. And if you want to, say, take everyday information and incorporate it into a scientific experiment in some way, you're probably going to have to change those measurements into metric units. It's also important because to some extent engineers still use the English system of measurement. Even if you buy a brand new engineering textbook, you'll find that there are a lot of example problems given in things like feet and pounds rather than meters and kilograms. And so if you're a scientist working with engineers, you might have to know how to convert between the English and metric systems. An example of that is actually given in the figure at the bottom of page 13 about the Mars Climate Orbiter. Some of the engineers working on that were using the metric system and some were using the English system. And along the way, somebody, I forget what it was, either somebody forgot to convert units or converted units incorrectly. And anyway, the thing went crashing into the surface of Mars, and there goes $125 million up in a puff of smoke. So yeah, unit conversions are important. Even within the metric system, even if everybody around is using the metric system, knowing how to do unit conversions is very important because when we're dealing with science, there's a certain subset of units of the metric system, which we'll get into in more detail in a few minutes. There are certain units within the metric system that are considered kind of the official units to use for things like equations, doing calculations. And unfortunately, as it turns out, those units are not always the most convenient units to use for doing measurements. So very often, scientists will do the measurements in a convenient unit and then convert them to the standard unit that they have to use to put the numbers in an equation. So you do have to know how to do conversions within the metric system too. Now within the metric system, it's pretty easy because everything is based on factors of 10. So once you know what the metric prefixes mean, the rest of it is pretty easy. So having built you up like that, we'll get into systems of measurement. Okay, so systems of measurement. Again, the main one used in the US would be the English system. And the English system, as most of us anyway are probably familiar with. I don't know if there are any Canadians in our midst, but Actually, even most Canadians are pretty familiar with the English system because the US media is so dominant. Um, so in the English system, you can do units of length. When you do measurements in length, again, as I mentioned a few moments ago, you have choice between inches, feet, yards, miles, and there are probably some others too, but those are the main ones. When using the English measurement for mass, actually you might say pounds, but there is a tendency, even among many scientists, to use the terms mass and weight interchangeably, but they're actually not the same thing. Mass is, and we'll get into this in more detail later, but just as a preview, mass is a measurement of the amount of matter in an object. And that actually never changes unless the object itself changes. And the actual English unit for mass is slugs. And you hardly ever hear about that. Engineers are pretty much the only ones that ever use that. And pounds would actually be a unit of weight. Or of course, you can also use ounces. Now, weight is related to mass, but it's not exactly the same thing. Like I said, mass is just the measurement of the amount of matter in an object, which means that it's not affected by gravity. So your mass would be the same here as it is on the moon. On the other hand, weight is actually a downward force caused by gravity pulling down on your mass. And therefore, weight actually changes with gravity. So your weight here on Earth would be different from your weight on the moon because the gravity is different. And pounds are actually a measurement of weight, not technically a measurement of mass. Since most of what we do is here on planet Earth, and, unless you work for NASA, you don't really have to worry too much about different gravity. We tend to use pound, mass and weight interchangeably, and that's okay as long as you stay on Earth. But if you're going to be talking about the moon or other heavenly bodies or someplace where the gravity varies significantly from what it is on Earth, then you got to be aware of the difference between mass and weight. Time in the English system is seconds, minutes, days, weeks, months, things like that. Temperature in the English system is measured in degrees Fahrenheit. A little ironic since Fahrenheit is about as German a word as you can imagine, but that is the unit used in the English system for temperature. And also there are derived units. That is, units that are obtained by combining other units. So we have things like area. Usually area is considered length units squared. So in the English system, that would be things like square inches, square feet, square miles, square yards. Those are all units of area because area is length times width. There is a special unit in the English system for area, which doesn't explicitly take the form of length units to the second power, and that is acres. Acres corresponds to a certain number of square feet, and I forget what the exact number is because unlike the metric system, it's not a convenient number, but it is a unit of area. And there's also volume. Volume is, if you have a regularly shaped object, it's usually calculated as length times width times height, and width and height are also types of length, so they would use the same units as length. And so volume can be expressed as length units to the third power, or length units cubed. So things like cubic inches or cubic feet, cubic yards, cubic miles, those would all be units of volume. And there in the English system is also a special unit for volume known as the gallon, or also fluid ounces. And those don't explicitly take the form of length units cubed, although they do correspond to a certain number of cubic inches or cubic feet. But again, the conversion is complicated because the English system is not based on factors of 10. Okay, so that is kind of an overview of the English system. Like I said, most of us are probably pretty well familiar with that from everyday life. Now, the metric system. This is the system that a lot of Americans are only vaguely familiar with. There was a push towards metrification back when I was a kid in the Stone Age of the 1970s. So we learned about it in school then. I don't know if they even teach very much about it now, and probably didn't stick with most people anyway. The metric system is familiar to basically anybody who has basically spent much time in Europe or Canada, or if you watch a lot of Canadian TV, you might be somewhat familiar with the metric system. Chemists actually use a specific subset of the metric system. Okay, so the SI subset of the metric system is an agreed upon set of standard units. The SI stands for Système International de Unité. You don't have to know that, but I'm just saying. SI stands for international system, but it's in French where they put the adjectives after the noun. So it's Système International. And what that is an agreed upon group of standard units for certain types of measurement. Like, for instance, if you're measuring something in the metric system with a ruler, you're probably going to use centimeters because that's what the ruler is marked off in. But the SI unit for length is actually meters. So you can take your centimeter reading and convert it to meters if you want to use that measurement in an equation. Okay, so these are basically standard units to use in equations. And the reason is that a lot of equations that chemists and physicists use are set up so that if you put in certain units, you will get out certain units. So if you put in the standard units for, say, velocity and mass, you will get out energy in the standard unit for energy, which is the joule. If you put in other units like centimeters per minute for velocity or grams for mass, then you're not going to get out joules for the answer for energy. Now, so as I said, we often use non-SI units, whatever units are most convenient, and then convert them to SI units if we have to use them in an equation. If you don't have to use them in an equation, then actually using non-SI units is okay. The standard, as we'll see in a moment, the standard unit for mass in the SI system is kilograms, but yet you will not find a laboratory balance that reads in kilograms. They all read in grams, because grams are the convenient unit to use for most things of the size that you would want to put on one of those balances. Okay, so the actual SI units are as follows. For length, you've got a lot of units in the metric system that you can use for length. when you start including the metric prefixes, you have a wide variety of magnitudes of measurement that you can use. You can use centimeters, but also millimeters, or even things like nanometers for measuring lengths. But the standard unit is the meter. Symbol for meter is a lowercase m, and 1 meter is approximately, and that's supposed to be a little squiggle there, it's a little muddy on the picture, is approximately 39.37 inches, which is approximately 1.1 yards. So if you've ever seen a meter stick, in a science class, you'll notice that it looks like a yardstick, but a little longer. And that would be 3.3 feet. Originally, the meter was defined as 1/10 millionth of the distance from the North Pole to the equator, passing through Paris, because the metric system was actually designed in France. After the French Revolution, they put a very high premium on reason, or what they regarded as reason anyway, and they believed that everything should be logical, and they tried to decimalize everything. And in some things, like measurements, like the metric system, it was actually a good idea, and it worked really well to decimalize things. They also tried decimalizing time, which actually didn't work out very well, and so we use the same system of time in the metric system as we do in the English system. But anyway, that's why they designated the distance from the North Pole to the equator through Paris, actually. Now it's actually defined by the speed of light. It's the distance traveled by light in 299 299,792,458 of a second. Okay, so that's a little harder to relate to, but it's more consistent and actually easier to measure, at least for scientists. Now, the well-known unit for that people often think of as a unit for weight in the metric system actually is a unit of mass. And so the standard unit of mass in the metric system is a kilogram, symbol lowercase k, lowercase g. And as I mentioned a moment ago, that is despite the fact that in the metric system, the lab balance is all reading grams, because grams are a smaller unit. A gram is about the size of, or is about the weight or mass, sorry, of a paperclip, whereas a kilogram is about 2.2 pounds. And we'll get to that in a moment. But for now, I will write down the difference between mass and weight so that you can get those. Okay, so mass, remember, is the measurement of the amount of matter in an object or a sample. And it doesn't depend on gravity. Weight, on the other hand, is a downward force and it's caused by the pull of gravity on your mass. Or the mass of an object or a sample. And that very much does depend on gravity. And in fact, they are directly proportional. This little equivalency, well, not proportionality here is what it really is, says that weight is directly proportional to gravity. The little symbol here is actually the Greek letter alpha. In mathematics, it means proportional to. So when we say weight is directly proportional to gravity, we mean that basically if you double the gravity, you double your weight. The gravity on the moon is 1/6 what it is on Earth, so your weight on the moon would be 1/6 of what it is on Earth. So that's what we mean by directly proportional. But as I said, we often sort of use mass and weight interchangeably, and that's generally okay as long as we are doing everything here on Earth. And 1 kilogram is about 2.2 pounds. These, actually, I'll point this out now, but I'm going to point it out again later. These conversions between the metric and English system, or between English and metric systems, are only approximate because these are two different systems of measurement that were set up according to two different sets of standards. They don't sync up exactly. So conversions within the English system are exact. 1 foot is exactly 12 inches. No more, no less. It's 12.0000 repeating on to infinity. And within the metric system, the conversions are exact also. 1 kilometer is 1,000 meters exactly. 1,000.00000 on to infinity. But because the English and metric system are based on different standards, they do not convert exactly. So that's why I'm being sure to say that when we draw an equivalence between the metric system and the English system, I use the approximately equal to sign. So 1 kilogram is about 2.2 pounds, but actually you could take the number out further than that. And you could keep going and going and going on to infinity, and the number just never stops because it's not it's not an even correlation. What this means is that 1 pound would be equal to 1 over 2.2 kilograms, or in other words, 0.454 kilograms. 0.454 is just 1 over 2.2. Okay. If you were to take a 150-pound person, their weight or mass in kilograms would be about 68 kilograms. And vice versa. A person with a mass of 68 kilograms would have a weight of about 150 pounds. Okay, so that's an overview of mass. Time. The standard unit of time in the metric system is actually seconds. And those seconds are the same as the English system. And this is what I was saying about, decimalizing time didn't work out very well. They tried that, didn't stick. So time is still in seconds. And, if you're timing something that goes on for a long time in the metric system, you can still use minutes and hours and days if you want to. It's just that if you want to use that number in an equation, you're probably going to have to convert it to seconds. This is the unit of 1 second is actually defined by the vibration of, by the radiation from cesium-133. That's a radioactive isotope of the element cesium, which gives off radiation. And so it gives it off at a steady rate, though. And so the time of 1 second is defined as the amount of time it takes for a certain number of emissions of radiation from this isotope. And the number is Let's see. Okay, so 1 second is the amount of time it takes for 9,192,631,770 periods of radiation from cesium-133. That's CS-133. You don't actually have to know that. It's just basically I was just telling you what it's defined as. In practice, we use the same relationships we do in everyday life. So 1 second is 1/60th of an hour. Or sorry, the minute. Or 1/3600th of an hour. That's 1/3600th of an hour. Because there are 60 seconds in a minute and 60 minutes in an hour. So 60 times 60 is 3600. Okay, temperature is where things get even more interesting. If you're familiar with the metric system, but you haven't taken a chemistry or physics class before, you would probably say, oh, temperature unit, that's Celsius, or maybe centigrade, because Celsius and centigrade are the same thing. But actually, it's not. The official temperature unit in the SI subset of the metric system is known as kelvins. Named after Lord Kelvin, who back around 1900 or so did a lot of experimentation involving low temperature things. And it's not Celsius. Because what we needed was an absolute temperature scale. Okay. And if you think about it, what we mean by absolute is that 0 means nothing. And in temperature, what you're measuring is actually the average kinetic energy of the particles in a sample. Because the particles, as we mentioned when we talked about solids, liquids, and gases, any particles in any object or sample are always constantly vibrating in place. Even if something is solid, like a piece of granite, and it seems like it's as immobile as anything could ever be, the little particles that make it up are actually vibrating in place. And those vibrations are because of the amount of thermal energy in the air, and the temperature is kind of a measurement of that thermal energy. As long as there is any thermal energy in the air, those particles will be vibrating, and there will be a temperature. The problem is that the Celsius scale and the Fahrenheit scale also have a situation where 0 degrees does not mean no thermal energy whatsoever. That's what you actually want. If you think about all of the other types of measurements that we do, whether it's length or mass or time, and it doesn't even matter what units you're using, all of those other measurements are absolute. So say in length, 0 inches really means no length at all. 0 feet means no length at all. 0 meters means no length at all. 0 pounds means no weight at all. 0 kilograms means no mass at all. 0 grams means no mass at all. 0 seconds means no time at all. But in temperature, 0 degrees Celsius does not mean no thermal energy at all. 0 degrees Fahrenheit, which is even colder, even that does not mean no thermal energy at all. the molecules are still vibrating. Not very fast, but they're vibrating. And so we need a system where 0 degrees really means no thermal energy at all. Okay, so let me write some of that down. Okay, so temperature is a measurement of the average kinetic energy of the vibrating particles in an object. And they're vibrating because of thermal energy. So heat causes the vibration. The more heat there is, the more vibration there is. If there were no thermal energy at all, there would be no vibration. And the average kinetic energy of the particles would be 0. But the problem is that doesn't correspond to 0 Celsius or 0 Fahrenheit. So we have defined the temperature at which there is no thermal energy, and the average kinetic energy from vibrations equals 0 as absolute 0. So that's what absolute 0 is. It's the temperature at which the average kinetic energy of the particles in a sample would be 0. In other words, the temperature at which it's so cold that there is no thermal energy at all, and the particles in the sample are not even vibrating. And absolute 0 would correspond to 0 on the Kelvin scale. And it's also equal to negative 273.15 degrees Celsius. So that's pretty cold, although Americans might appreciate this next number even more. It's negative 459 degrees Fahrenheit. So that is really, really cold. Absolute 0 is also the coldest temperature possible. It means no thermal energy whatsoever, and there's really no such thing as negative thermal energy. Okay, so this is the coldest temperature possible, even in theory. And something important to remember, the implication of that is, since you can't go below 0 on the Kelvin scale, there are no negative temperatures in Kelvin. And keep that in mind if you're doing a calculation like you're trying to change a temperature from Celsius to Kelvin. If you come up with a negative number for Kelvin, you definitely did something wrong. So keep that in mind. It's also useful to remember that each degree on the Kelvin scale is the same size as 1 degree Celsius. I put the word degree in quotation marks here because technically on the Kelvin scale, you're not supposed to call it degrees Kelvin. It's just kelvins. And you notice I didn't use a degree sign up here at the top. I'm not really very picky about that, but it's just something that you might want to keep in mind. So what this means is that temperature changes or differences would be the same in Celsius and Kelvin. And that can actually save you a little bit of time. There are some, because Kelvin is the standard unit for temperature, you do have to use kelvins for measuring temperatures in all kinds of equations, but it's possible that you can save a little bit of time. If the equation calls for change in temperature, then you can just use it straight in kelvins because the change in temperature in Celsius would be the same. It's only if you need individual temperatures that you have to change from Celsius to Kelvin. Okay, I see we've gone over the half-hour mark a little bit here, so I'm going to stop there and go on to part B for the rest of this. Oh yes, one thing I will say though is I'll give you the conversion. Temperatures in Kelvin are equal to temperatures in Celsius plus 273.15. Oh, okay, never mind. There is an absolute temperature scale that corresponds to Fahrenheit, but sometimes engineers use that, but nobody in chemistry cares, so I'm not going to confuse you by putting that in here. This is the conversion. We'll do some examples with that in a little while, but for now, I'm going to break for part B. See you in a moment.